So far we've talked about Boyle's law, pressure and volume. So in your simulation that you were working on Tuesday, you were looking at temperature. So you had that hot plate, kept turning it up, and we're looking to see what happened to the volume of a gas. So as the temperature went up, hopefully your volumes went up, and your graph looked different from Boyle's law because it was a different relationship. So for this one, it is T and V. We're not picky that you know the names of it eventually. If you go into advanced chemistry, they may want you to know the names. But all we care about is you understand the relationship between temperature and volume. So this is different. It's a direct relationship. So that means if temperature increases, volume increases. It does the same thing. So I'm going to post a video on here. Normally at this point we would have watched it. If you want to watch it, you can. You don't necessarily have to. It's the Leonardo project and Charles' law. So what happens in particles were heated, and on that something has to change. So an example of this is if you put a marshmallow in the microwave. If you have one, go try it. If you haven't done this before, or from Easter you might have a little peep or a bunny or something like that. You can do it. So you put it in the microwave, it heats it up on there. So what we're going to see happen on here is that volume's going to increase. And the reason why is it wants to maintain pressure. I guess I didn't really need that little up arrow there. Okay, so volume increases instead in there to keep constant pressure. So Charles' law is always at constant pressure. So when you did that simulation yesterday, the pressure was always on the same thing. So we said a marshmallow in a microwave would be an example of it. Another example in here would be a helium balloon. When you buy a helium balloon and it's a really cold day outside, you go outside and it looks like they didn't put enough helium on it. I remember when my older daughter was little, my parents bought her a balloon and we went outside and she said, "My balloon's broken," on there because she saw it shriveled up. But when we took it back inside, it was fine. So if you were having like an open house or party or something in winter, you'd want to make sure to ask them to add a little extra helium in the balloon because you know outside it's going to shrink. But in summer, you have to be careful. A lot of times when there's a party, a balloon will just pop out of nowhere. And it's because those particles in there start moving faster and faster. They want to expand on there, and there's only so far they can go on there. And again, the reason why is to keep that pressure from being too much. So eventually, it just has to pop on there. Okay, so we have an equation. You can write this one two different ways. So the first way you can write this is V1 over T1. Now this looks different from Boyle's law. It's going to be equal to V2 over T2. So Boyle's law, the ones were together and the twos were together. Now they're going to be stacked on top on here. Okay, so you can cross multiply this, and there's multiple ways you could write this. So you could write it V1 T2 is V2 T1. You could write it T1 V2 is T2 V1, and there's even more possibilities from that. So the only thing that's important here is if you cross multiply, the ones and the twos need to be paired up the oppositely. So if V is a 1, T is a 2. If V is a 2, T is a 1. You could even take this equation and say T1 over V1 is T2 over V2. It doesn't matter, just that relationship needs to show that if volume goes up, temperatures goes up. That VT relationship is proportional. That's what you should have seen in your simulation you just did. So one of the questions on our gas self-discovery was, why is Kelvin better in here? So we want our temperature to be in Kelvin, or just K. And that is because Kelvin starts at 0. It's called an absolute scale. So absolute 0 is the lowest one. You will never have a negative temperature in Kelvin. Celsius you would, though. Well, think about if you plug that in this equation and the T's were negative, you'd be getting negative volumes. That wouldn't make any sense. You can't have a negative volume on there. So that's why we need to use Kelvin. The volumes must match. They're going to be in units like liters, milliliters, or centimeters cubed. Liters and milliliters are more common than there, but it could be in the cubic centimeters. And it doesn't matter which way, they just have to match. So if it said a gas at 150 milliliters goes to 2.1 liters. You could either say 0.150 liters, or you can move it over and just make that milliliters instead. Okay, so I guess I went ahead and I put those up there. So either way is fine on how you want to do that here. Okay, so we can also then, if you want, just put those numbers at the bottom. I just forgot to do that. Okay, so on here, so again, if you'd rather, you can go ahead and have those on there. It doesn't matter to me. Okay, so let's look at some problems with this. So again, our equation, I like the proportion way. If you want to multiply it out that way first, that's totally fine with me, but I like to leave it lined up. And again, this could be flipped in different ways, but the important part here is that on your diagonals, a 1 would be with a 2. So there's different ways you could write this. So number one thing you have to do on anything where temperature's in it is make sure that it is put in Kelvin. So notice on here, this is 88, and that's not what we want. We need to put that into Kelvin. So to do that, remember, we're going to add 273 to it. So this instead then is going to be 361. And then we're also going to take 273 and we're going to add that to the other temperature, which is 70. Okay, so that temperature is going to be 343. Again, make sure your numbers make sense. 88 is bigger than 70, so this should line up that way as well. Find the new volume, so that means we're looking for V2 if it started out at 223, and sorry, that's missing a T. Okay, so what we need to do here is plug in V1. That is 223. T1 is where we started, but again, use the Kelvin one, so 361. New temperature is what we converted that one to, and that is 343. So think about here that, oh shoot, let's see, that should be on the bottom. Sorry about that. Okay, so that's actually what we don't know here, V2, and then 343 is here. So we know our temperature is cooling, so that means our volume should take up less room as well. So T and V always do the same thing. Another thing that uses this technology I forgot to mention earlier, you might have a big green egg grill. We have one of those, and it has this little flume thing that you open, like a chimney kind of thing, on there. And so to control the temperature, you either open it or close it more. So the bigger the volume of air, the hotter your grill's going to get. And if you need it, if it's too hot, you just shut it a little bit more. Less air is going to make the lower temperature on it as well. So we're going to cross multiply, and again, this is all I need to see in this problem. You always want to start with the two numbers that on here don't have a variable. So this side is what you always should be putting in your calculator first, and then afterwards, whatever's with the variable, that's what you're going to be dividing by. So what we need to do here, and again, I don't care if you show me this part, I just need to see the first part and have you do this correctly. So 223 times 343 is equal to V2 times 361. So again, this is an optional step. If it helped you to write it, do it. Okay, then on both sides, we're going to divide this by 361 to do that. So again, some people like to write everything down. And if that's you or your math teacher's that way, go for it. Don't round on here, though. We want to write out every number if you're doing it that way. So if you're doing it that way, 76,489 is equal to 361 V2, and then you divide by 361, just like I showed you before. So now I'm going to hit divided by 361. So if this were me, I would just type 223 times 343, and then I divide it by 361. Either way, it's going to work out. All right, so we get 211.88, blah, 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 a lot more numbers in here. Just be reasonable on your sig figs here. Your Kelvin temperatures all have 3. Your other volume has 3, so it makes sense to round this one to 212 milliliters. Think about if your answer makes sense. Your gas cooled. It was at 223. It didn't cool that much. It just went from 88 to 70, which in Kelvin is 361 to 343. So it shouldn't be that much lower. So let's talk about how to draw this. Your first picture would be a bigger box. Your second picture, this is before, this is after, should be a little bit smaller box on there. And you aren't changing the gas. This would be a sealed container on here. And whoops, that's not what I wanted to do. They've changed some of these icons on here a little bit, and they're not quite what I'm used to. Let's see, here we go. Okay, and so I'm just going to make my dots green. So I always want to see at least 4 dots, and gases, like to spread out to fill their containers. So let's go ahead and do that. Now we said there's constant pressure, so the easiest thing to do here is just not to draw any pressure on here. So what I like to do on this is just not draw them hitting. If you want to draw all of them hitting, or if you want to draw half of them hitting, as long as it's the same, it's fine. So when this has a bigger box, it's because these particles are moving faster, and so they need more room. This other box, they're not moving as fast. So it doesn't need to push out as much as the other one does, because again, the goal is just to maintain your pressure to keep it the same. So I want to see box 1 being bigger and particles moving faster. When they cool down, they don't need as much room. They're just trying to keep that pressure up. And that's all I need to see. Okay, so our next one on here, we are looking for temperature instead. So we see our 2 volumes, so it's 2.0 and 3.0 liters. And then we have a temperature, and it wants to know what is the new temperature. So let's go ahead and put this in, and again, V1 over T1 is V2 over T2. So we're starting out at 215, but careful, that's the temperature. So again, usually put it on bottom. If someone flipped it, if they're both flipped, it would be okay. It was 2.0. It's going to go to 3.0. And then we're looking for T2. So our temperature goes up. It's going from 2 to 3. So that's 50% bigger. So I know my new temperature should be about 50% bigger. So think about what's about 50% more, or 1.5 times 215, to think if your answer makes sense here. So I'm going to take, and again, many ways you can cross multiply here. So I'm going to take 215 times 3.0 is equal to 2.0 T2. If I want to go ahead and multiply the 215 times the 3.0, that would be 645. And then we're going to divide by 2.0. But all you really need to show me is what's here and be able to put in your calculator. That's fine. So now we're going to take 645 and we're going to divide it by 2.0. You can really just type 2 in your calculator if you want. And so our new temperature is 322.5. The volumes just have 2, but this is a temperature. So I'm going to go ahead and round this to 323 Kelvin. If somebody said, well, I'm just going to put 2 since that other one had 2, I'm fine with that too. I'd also take 320 Kelvin. Okay, so this time our new temperature is higher. So we'd want to see the opposite here. These particles aren't moving as fast. These are moving faster, so it has to spread out so to maintain pressure. So again, the easiest thing to do when pressure is constant is just not show it. But you could have all 4 of these hitting. You could have 2 hitting in each picture. Gas shouldn't change because we're still under the same things. It's just something like that simulation where you can change the piston. Okay, so now it's up to you. If you just want to do notes today and worry about the quizzes tomorrow, you can keep going the notes. If you want to stop here and then practice that law while it's fresh in your mind, you can. So again, your reminders and lists, temperatures need to be in Kelvin. Your volume units need to match, so watch out for problems on milliliters and liters. And then just illustrate it accordingly if they asked you that. So temperature is number of whooshies, how fast they're moving. Hotter particles move faster. And then volume is the size of the box. And again, we're not looking for things to be perfect on your picture, like, oh, this should be 2.5 times as big. We're just looking for the bigger or smaller thing. But it's good if it's just a tiny change to not make it as drastic. And if it's a huge change, make it look more. Okay, so again, if you want to stop here, that's fine. If you want to keep going, then come to the next slide. All right, so we have another law now, and it's Gay-Lussac's law. Sometimes it's called the Hamilton's law too, but we usually use this term. It's what the book uses. So Gay-Lussac's law is also temperature, but this time it's pressure instead. So think of something that heats something up and causes pressure. Maybe you thought popcorn. The big appliance now is the Instant Pot on there. and it has a seal around it, and that it allows you to use pressure to get your food to cook a lot faster instead of something like a crock pot that takes a lot longer. So when things are moving fast on there, think about if you had like beads in a container and you're shaking them. The faster you would shake them, the more they would hit the walls in here. Okay, so what we'll put in here is when temperature increases, so does pressure. This also matches. So hot particles move quickly, which causes them to hit the walls more, to collide more with the walls. So more collisions on there. Okay, so if something's moving slow, it's not going to hit the walls as much. Where if things are moving faster on here, you're going to see them bouncing off more. So what I should see is lower temperatures, one line not hitting the walls as much, higher temperatures, two lines and bending more. So these match, so this is also directly proportional. And again, makes sense. Faster something moves in there, if you shake it or throw it or make it move faster, the more it's going to hit the walls. So some things we see in here, on a hot day, tires blow out. And like I said earlier, you can cook, that's missing cook, goodness. Dinner quickly in the Instant Pot using pressure. So the actual food cooking takes hardly any time at all in there, but it takes a little bit of time to get it up with that pressure on there. So one thing that some people do sometimes is they turn it on and they hit the saute button, and that uses more of the conduction, the heating of the actual device with the hot element in there. And then they transfer that heat. So heat can be transferred just like you can, E equals MC squared or some of those things where you can transfer things, or like the LOL charts we did for that. Okay, so like before, we've got to remember a few things on here. So we want to know that everything's in Kelvin, and then our pressure units need to match. This year we skipped pressure conversions because it's just in too much time. We have such little time left. You're already about halfway through learning already. So sometimes pressures will need to be converted just like you converted centimeters and inches, but we're not going to mess with that this year. If you find one like that, let me know and I'll tell you how to do it if that accidentally gets in something I forgot to change. Okay, so our equation is going to look a lot like the other one. So we're going to have on here, P1's on top. Sorry, it's supposed to be a P. And then T1's on bottom is P2 over T2. So again, you can multiply it out if you like that way better. But I like to keep them like this. So my starting are lined up in that. And again, you could put T1 over P1 is T2 over P2, but we're going to do this combined gas a little later, and we kind of usually keep things to look like that, and that's why we do it. Okay, so on this one, find the pressure if it started at 11.3 psi. So that's P1. We don't know our new P2. 331, and it's already in Kelvin, and it's cooled to 310. So right away, you should be able to tell me here that on this one it cooled down, so the pressure shouldn't be as much. So you just think if you're going to take your finger and kind of trace back and forth, hitting the sides on something, if you go super fast on there, you would be hitting it a lot. Or if you're shaking something like that, would see that. Okay, so we're going to take 11.3 times 310. It's going to be equal to 331 times P2. And then I'd have to divide both sides by the 331. If I want to write down my answer first, it'd be 11.3 times that's 310. I don't know why I put a decimal in there. Okay. So I'm going to take 11.3 times 310. That's going to be 3,503. So again, if I prefer to write it that way, I can, but I'm not going to make you. So divided by 331. And again, if you're multiplying it all out, write all the numbers, we'll round at the end. Okay, so I see here 10.58, a bunch of numbers. So everything on here started out with 3, so I'm just going to round that to 10.6. And then in here, this was in PSI, so that's what I want to label it, match your pressure unit that they gave you. So the gas is cooled. If I look at my pressure now, it was 11.3, now it's 10.6. It was on here 331 and it dropped to 310. Let's go over how to draw this. So your boxes are the same size, so you want to do your best to make these exactly the same size. And again, if you're not sure, I'm going to be able to tell. You might want to write same size. I don't want to see like a box like this and have you write same size. But if they're close like this, if you want to write same just to make sure I know what you're talking about on here, then you definitely can on this. Okay, so if we look at this problem before, okay, so it was 331 and it dropped to 310. So we're going to make it bigger. And that hit the walls more. You only want to hit the walls and bend it if it's hitting the wall. And everyone doesn't need to hit it, so I could have like one in the middle here that's going straight. Over here, these are slower. So I want to show these not hitting as much, but it's fine to hit them one. I usually hit everything at least one with this law on here. So here, the temperature dropped, and so did the pressure. All right, one last example. So we're going to do the same thing here. So this time our pressure goes up. So I'm going to put 15.4 here and 19.2 here. Find the new temperature. If it was 343, check that it's in Kelvin. It is. So what we don't know now here is T2. So I can cross multiply. Okay, and again, if you want to write all that, you can. The only thing I need to see is this in an answer, though. 343 times 192. And divide it by 15.4. And again, number one thing to watch out for here is, does my answer make sense on here? So I'm going to take 343 times 19.2. And then if I want to write that down as 6585.6, and again, don't round here, wait till the end. And then both of these have to be divided by 15.4. So the easiest thing to do here is just take 343 times 19.2, get that answer. And again, you don't have to write it down unless you want to. Divide it by 15.4. 427.6. So the other temperature was just a whole number with 3. So everything in here is 3. So that's my best rounding here. So this is 428. And then this is Kelvin. So in this one, my temperature goes up and my pressure goes up. So that's how we're going to draw it. Again, same size boxes. So you do your best to make these look the same. Same number of dots because we didn't add or remove anything. So these are moving faster, and if they're moving faster, sorry, this is kind of hard to do on an iPad, then they're going to hit the walls a lot. Here, not as much, only one arrow. So when you heat something, it's going to be bouncing around more than something that's slower and isn't going to bounce as much. So that's what we should see here. T increases, P increases. Okay, so to wrap it up, you do have a Canvas quiz on this law. We will then look at some conceptual videos later this week and kind of see what happens. We will take an actual quiz on some of these gas laws, and then we'll have 2 more to do. The combined gas law, which just instead of having 3 and you get the 4th, we'll have 5 and you get the 6th, and then another law called the ideal gas law will be what's left. If you have any questions, let me know. Thank you.